Harvard, and he'll tell you about his research, so I won't attempt to preface that or summarize it, but he's from St. Louis, from the Midwest, and he was an undergraduate major in engineering, electrical engineering and engineering physics at Case Western Reserve, and it's been delightful to talk to you today, and we're very glad to have you with us. Thank you.
Thank you very much, Lee, and thank you everybody for coming. It's a lot of fun to be up here today, and I've had a lot of fun talking to some of the students and the faculty here, and I'm very excited to hear about a lot of the energy stuff that's going on here. I think it's very much on the forefront right now. So today I'm going to talk about energy, actually, and I'm going to do that in the context of the first part of this title, which is to extend silicon's reach, which sort of might beg the question of why would we want to extend silicon's reach in the first place, especially in the context of photovoltaics. And in that arena, silicon actually is a good success story. If you think about some of the limits for how we would convert solar radiation into energy, silicon does a very good job of it. It's manufacturable. It's widespread. It's everywhere you look. But it has a lot of defects when it comes to solar energy, and that's pretty much evidenced by the fact that you don't see it in a lot of places, and that is that it costs a lot. It's expensive to manufacture, and cost is a function of both just the raw cost of processing a kilogram of the material, but also how efficiently it can produce solar energy at that given cost. And so I hope by the end of the talk today I can convince you that we are onto a technique, which is the second part of my title, the non-equilibrium doping, that could help us take this material that is a real winner in so many senses and really add to its capabilities in the photovoltaics arena. So as I mentioned, this talk largely revolves around solar energy. And one of the reasons solar energy is a compelling energy source is simply because of its abundance. So the rate at which we receive energy from the sun overdoes how quickly we use it by a factor of about 10 to the 4. So this is frequently hammered over people's heads in solar talks. It's almost like a law, if you see a talk on solar energy, to show some sort of map that shows how small 1 over 10 to the 4 is by showing you what 1 over 10 to the 4th of the Earth's area is. And I often think that's cute and it's instructive. It's important that it's much larger than our energy need. But as anyone that looks at global resource constraints would be familiar with, it's not necessarily the quantity of a resource that is important to us, but rather whether or not it's economic or reasonable to assume that we can scale up to capture that energy. So I also like to show a map. I don't want to break any of the solar laws here, but I like to show a slightly different one. And so this is a map of the United States that shows how we use land for various purposes. And I've color-coded it so that in green here we're seeing the area, approximately 30 to 40% of the United States that we devote to farming or pasture land or some sort of agriculture. That's a large area of land, obviously, but it might not represent the scale of a comparable scale of investment, because a lot of this land just has to be managed, not built upon necessarily. So in Ohio there, which is where I went to college, which is as cold as Hanover, but much grayer. It's sort of a more depressing place, maybe. That's about 1% the land area of the United States, and that represents, if you put all the things that we've paved over, so highways and buildings and arenas and swimming complexes and things, if you put those all in one place, they would cover a land area comparable to the size of Ohio. And then over there in the great state of New Hampshire, this is the area that you'd have to cover with moderately efficient solar cells to power all the electric and transportation needs in this country. So about 75% of our total energy usage. And that's accounting for the relative shadiness of New Hampshire, the nature of the sunlight, and also the efficiency of a normal solar cell. And this map is a little more indicative of the scale of investment, I like to think, of what a project like that would represent in human terms. It says nothing about cost, but it says something about capability. This is certainly something that given the right economics, is more than doable. And I think that's maybe a more relevant thing to keep in mind when we discuss solar energy. So why do we not do it? Of course, and I've already said this several times, it's cost. So if we want to think about cost, which is sort of this mix of factors, one big one is efficiency. And so to do that, I'd like to start with just a really kind of general model and picture of what are the limits to solar efficiency, to converting the light coming from the sun and that we can convert into useful work. So in general, this simple system will always include the source of energy, which is the sun, which is a black body radiator. We can say exactly sort of how it radiates. And we were going to absorb that radiation with some black box. And we're not even going to say what it is yet, but if it can absorb this radiation, it will heat up in general to some temperature, which we'll call TA for T absorber. And we can actually describe the rate at which energy flows into this box and the rate at which energy flows out of this box with well-known equations. They're not particularly important, and I won't dwell too long on equations, but we can get some interesting results if we think about it like this. So these are just the Stefan-Boltzmann laws. So this is that the energy coming out is just a very simple function of temperature. It's a constant times temperature to the fourth. The energy going in is actually very similar. It's a constant times T to the fourth, where T is now the temperature of the sun, 6,000 Kelvin. And there's this additional geometric factor, C naught. And this just accounts for the fact that the sun takes up a very tiny fraction of our field of view. So if you walk outside, the sun is about a 1,000th of a percent of the field of view above you. So outside, it would be about 10 to the negative 5. If you had a big lens, you could make it much, much larger than that. You can get up to 1,000 pretty easily, or 1%, excuse me. But you can't get that number larger than 1, essentially. Otherwise, you could heat it up hotter than the sun, which thermodynamics tells us isn't really possible. So we can say that in thermal equilibrium, the heat in will equal the heat out, and we can predict the temperature of the sun very easily. It's just it's equal, or the temperature of the absorber, excuse me. It's just equal to the temperature of the sun multiplied by this geometric constant raised to the 1/4. So if we plot that as a function of that constant, we get a curve that starts at a couple hundred degrees and goes all the way up to the temperature of the sun. It's useful to note right here that getting to about right here on this plot is pretty easy. And it can be done, if you want to fry some ants or something like that, you can do this pretty easily. Of course, we're not just interested in heating up a black box. We would like to extract work from this. So we can hook up some sort of arbitrary heat conversion device that will convert this heat into work. We're not going to say what this is yet. It could be a heat engine. It could be a chemical battery. It could be a plant doing photosynthesis. The only things we have to define right now is that it can do work, but it has to eject heat. Thermodynamics tells us that you can't just turn heat into work. You have to eject some heat somewhere too. So we can look at this still very general system and define an efficiency, which is just the work out over the energy in, which is very well defined in terms of all the things we've written down up there. So just the energy in minus all the other energies we have to eject over the energy in. And in fact, all of these have nice forms up here, except for the waste heat. So we're going to go ahead and write that down. And this will be as mathy as the talk gets. But the important thing to note about this equation, which is at this point totally independent of how we convert this energy into work, the only real free variables here are this waste heat, which is going to depend on the kind of engine we choose, whether it's a heat engine or something else, and this geometric constant right here, C naught. So it's interesting to consider the best possible efficiency that we can ever achieve. And for anyone that's a fan of thermodynamics, you would know that the best possible efficiency is the reversible efficiency. And for those of you that aren't fans of thermodynamics, all this means is that the entropy production has to be 0. So the entropy in has to equal the entropy out. And if that doesn't mean much to you, don't worry about it. All that you have to know is that that this equation down here at the bottom for reversibility constrains that equation. So we can, if we write down that all those have to equal 0, we can solve that equation above for the efficiency. And that gives us the thermodynamic limit of solar energy conversion. So regardless of what you replace this question mark with, this is the best efficiency that you could ever achieve without breaking the laws of thermodynamics. So we see that without concentration, that number is around 75%. With concentration, you can get up to the efficiency you might expect operating a heat engine between the sun and the earth, which is around 95%. Of course, we know exactly what we're going to replace that question mark with. We're going to replace it with a photovoltaic.